Balanced cross-sections are important tools for investigating interpretations of complex structures such as fold and thrust belts. But how do you go about balancing a cross-section? We can investigate how cross-sections are balanced using this example from the Central Appalachians, which comes from a classic paper by Gwynn from 1964. These are his diagrams, and we'll be looking at the lower of the two cross-sections we can see here. At the end of this presentation, I'll say a few words about Gwynn and this paper. But for now, let's go back to the coloured version. Notice the scale on the right, and we'll talk about the stratigraphy in a minute. But what are the assumptions behind balancing the cross-section? Well, we're going to assume plane strain. In other words, all the displacements and deformation occur within the plane of the cross-section. And we'll also assume that the bed length is conserved from the deformed to the undeformed state. Finally, we'll assume that the stratigraphy onto which we'll make our restoration is layer cake. In other words, it keeps constant thickness across this area of interest. So there are two main fold structures at outcrop, the Browns Mountain anticline and the Wills Mountain anticline. And they're two broad stratigraphic packages. The younger rocks which we see at outcrop are largely of Devonian age, and these are underlain at depth by a thick panel of carbonates that are mid-Ordovician down to lower Cambrian age. The structures are interpreted as having detached on a regional detachment horizon or sole thrust, which lies just beneath these carbonate rocks in an incompetent shale-dominated unit. But you'll also see that there's an important detachment horizon that decouples the shallower Devonian strata from the underlying carbonates. Well, these are the components that are in Gwynn's interpretation. And we're going to assume that the stratigraphy originally was of constant thickness across the area. So our task is to restore the structures that we see in the deformed state section in the modern day at the top onto its pre-deformed state below. We'll set up on the left there a pin line, and on the right we'll set up a loose line. If the section is to balance, the loose line, when we restore its position on the restored template below, should be vertical and unbroken. In other words, all our bed lengths should restore to the same original length. Okay, let's get going. And we're going to start off by restoring the carbonates at the base of the section. So we can measure in from the pin line, along the base and along the top of the carbonates and report these measurements back on the template below here. So now let's continue along measuring the basal carbonate unit here and restore those lengths here and find the position of the loose line over there on the right. I've marked on where the two thrusts occur with those pink blobs. Let's do the same now with the top of this carbonate package here and restore those measurements back onto the template here. Well, we can see straight away that the top and base of this carbonate package restore to different lengths. In other words, the cross-section does not bed length balance. So let's look at the mismatch. We can use this to modify the interpretation above to achieve a balance. So what we could do is simply increase the section length of the base of the carbonates by altering the interpretation above. And one way to do that is to move the detachment level up so that it occurs at the base of the carbonates. So let's look at these two areas here and change the interpretation like this. And in doing so, we've increased the length of the base of the carbonate package. So let's go and restore this again. Here's our restored template. We can put on the top of the carbonate package like this and restore it as we did before. So now let's make our new measurements for the base of the carbonate package here and put all these measurements back onto the template below. And we can see we've done a pretty good job. And now the top and base of the carbonates have the same length. In other words, the cross section for this stratigraphic level balances. But what about some of the other stratigraphic units? Well, let's look at this lower Devonian formation. We can measure its length sinuously around the folds and put it onto our restored template. Here. So this doesn't balance with our new interpretation for the underlying carbonates. Let's go back to our original interpretation and its restoration for the underlying carbonates. So in our original interpretation, the carbonate top is too long with respect to its base. And it's also too long when compared with the lower Devonian mark we've just restored. So maybe we need to change the interpretation for the top of the carbonate layer and reduce its restored length. So let's look at these two parts on the cross section, in other words where we extend the long footwall panel beneath the overriding thrust sheets. So let's modify our interpretation now, here. And now we can try and restore this. That was our original mismatch for the carbonates. Here's the base of the carbonates, which we retained from our original interpretation. And here is the top. And let's check its measurement there. So by changing our interpretation, we can get the top and base of the carbonates to match, and they also match with the overlying lower Devonian. So the section balances for these three stratigraphic levels. So that is a balanced section for three horizons, but there's actually another horizon in here that we've not considered yet, which I've labelled the top Martinsburg. So let's check to see how this performs. Again, we can measure sinuously around its length on the cross section and lay it out flat on the restored template. And the top Martinsburg is slightly too short compared to our other three horizons, which do restore. So let's now change the top Martinsburg interpretation in this area here beneath the Browns Mountain anticline. By increasing the displacement on that thrust which offsets the top Martinsburg, we can increase the restored length of the top Martinsburg. So let's do that. Here's our revised interpretation. Let's measure it up and now restore it. So now, by changing the interpretation within the Browns Mountain anticline, we can complete an interpretation that fully restores, and all four horizons now have the same length. So this modified section balances. We can do a bit more now. We can actually show where those thrust trajectories plot on the restored section here. So we can see we've got a basal detachment running in the lower Cambrian stratigraphy at the base of the section below the carbonates, climbing up through the carbonate layer. And we can also see we've got a detachment within the Martinsburg that stacks up the younger Ordovician and Devonian strata that overlie it. So now we've got a balanced cross-section, we can compare the lengths of the restoration below with the present-day cross-section to estimate the orogenic contraction that the section records. So let's make sure our pin line is aligned over there on the left. And now we can simply look at the offset of the loose line on the diagram. And it's been moved in from the original length to the final length by some 4.5 kilometers. But notice if we use the length of the tops of the carbonates in the original interpretation, which restore over here, our estimate of orogenic contraction would be increased by a further 3 kilometers. So the orogenic contraction we estimate is fundamentally dependent on the interpretation on the cross-section. So that's our balanced cross-section. We must emphasize the assumptions. We restored our cross-section onto a layer cake template. We assumed plane strain, and critically, that bed length was conserved. In other words, these rock units have no distortional strain within them. If this assumption of bed length conservation is invalid, then this revised interpretation for the structure on the cross-section could well be wrong as well, and we'd need to apply rather more complicated restoration techniques. So it's always important to state these assumptions when we come to balanced cross-sections. Well, let's go back to Gwynn's original diagrams. These cross-sections from 1964 are really surprising. They come from this paper published in the Bulletin of the Geological Society of America. And Gwynn was one of the first people to really demonstrate thin-skin tectonics, in other words, the importance of thrust detachments, in the development of the valley and ridge in the Central Appalachians. In the early 1960s, Gwynn had worked for the Mobil Oil Company, and he was able to integrate a vast number of exploration wells, exploration for gas, in the valley and ridge and the surrounding plateau of the Appalachians. And this shows some of the work that he was able to integrate together. You can see there on the left the number of well penetrations in some of the structures. Gwynn is something of a forgotten figure in Appalachian and indeed thrust belt geology. In Gwynn's short career, he'd moved from Mobil onto a series of academic jobs and had just been appointed to the department chair in the University of South Carolina when he was killed when the trench he was working on during a research project in Louisiana collapsed. He was 33 years old. His early death was a great loss to structural geology, but he left a legacy of these remarkable cross-sections through the Central Appalachians.